Hello, my name is Edmond Adib. I'm a PhD candidate at ECG department at UTSA, University of Texas at San Antonio. My research area is using generative algorithms in deep learning to generate synthetic biomedical signals, such as ECG signals. My advisor in this project is Dr. Jeff Privast, an associate professor at ECE department at UTSA. My co-advisor in this project is Dr. Fatemeh Afqah. She is an associate professor at ECE department at Clemson University. ECG signals are in fact time series. There is a pattern associated with each heart condition. So by looking at the ECG signal, the expert can diagnose the heart condition for the patient. So the ECG diagnosis is usually done by human experts, which is prone to random human error and also time consuming. The automatic ECG signal diagnosis is done usually by machine learning and deep learning models. Automatic ECG signal can eliminate the randomized human error, and also it can be available online or very cheaply at home. ECG datasets are usually highly imbalanced due to the abundance of normal cases and scarcity of abnormal cases. Also, ECG signals is considered as private information, so its use is very restricted. So by generating synthetic ECG signal, we can resolve both issues of the scarcity and also the privacy of the. In this slide, some samples of generated synthetic ECG signals are shown, 7 classes, and as it can be seen, the pattern in each class is very different from other classes. The dataset that we use in this study is from MIT BIH arrhythmia dataset. This dataset is available on PhysioNet website. It has 48 records and also very highly imbalanced. The signals are continuous digital signals, so our models are required individual bits, so we need to do segmentation on these continuous signals. We use adaptive window method for segmentation, in which we measured the forward and backward distances between our peaks and so used the 75% of each as the cutoff distance to break up the continuous signal into individual signal. After the segmentation of the whole data set, we get more than 100,000 individual bits in 15 different classes. As it can be seen, it's very high imbalanced, and more than 75% of the bits are in one normal class, and in some classes we have just a few number of samples. Here I'd like to mention the difference between the embedding in critic and the generator. The embedding in generator is element-wise concatenation, while the embedding in the critic is channel-wise concatenation. We use two parallel inputs as two different channels as the input to the critic. This table shows the number of samples that we picked from the original data set, and also the number of data in each class that we used for training, and also the test data set. It must be mentioned here that the test data set is the same for all the classification that we used in this study. We generated data in two different scenarios, screen data and unscreened data or raw data. In raw data, we use all the generated data regardless of the quality, while in screen data, we measured the distance of the generated sample with the template. If the distance was more than a threshold, we discarded the data. So we created 4 study cases, conditional GAN raw, conditional GAN screen, unconditional GAN raw, unconditional GAN screen. We compared the study cases in 2 different ways. The quality of data, we measured the average distance of the generated data with a template, and also the authenticity of the generated data. The authenticity authenticity test is done in the classification test. This table shows the average distance of the generated data and also the real data in each class from the template. As we can see, the screen data has a better quality, meaning that the distance between the average distance between the generated data and the template is less than the unscreened data. And there is a reason for that, because the bad quality data has been already discarded. For the authenticity of the generated data, we used the classification test. So we first trained our classifier on highly imbalanced real data sets. The classifier that we used was ECG 34, which is the state-of-the-art classifier. The metrics that we used to compare was micro-average precision score, multi-class precision recall curves, and also net improvement in the true positives. All the other cases are compared with the reference case. So the reference case is augmented and balanced with the synthetic data set. So we generated data set in 4 study cases. So we get 4 augmented data set. Then we trained our classifier, the same classifier, on each of these augmented data set. And then we compared the metrics. These are the confusion matrices for the reference case and also the 4 study cases. So the case 3, by looking at the numbers, case 3 has a better result so far. In this study, we are interested in maximizing true positives, meaning the samples that can be classified correctly, and also we want to minimize the false positive, the number of samples that are classified as correct wrongly. So we want to minimize false positive over true positive. So precision score is the metric that we want to use rather than recall. And the precision score, micro-average precision score, favors case 3, which produces the highest average precision score. Another metric that we used was the multi-class precision recall curves. As we all know, the objective here is to maximize the area under the curves, and as we can see from the curves, study case number 3 produces the maximum area under the curve. The other metric that we used was the net improvement in true positives. So the diagonals on the confusion matrix show the true positive. So we subtracted the true positives, the diagonals, from the corresponding elements in each case, and we summed them up algebraically. Using these metrics in the total and also in minor class shows that the study case 3 produces the best results. So to sum up, in this study we developed 1D auxiliary classifier Wasserstein GAN with gradient penalty model. We generated data in two models, conditional GAN and also unconditional GAN. 7 models for 7 different classes. And also we generated data in 2 scenarios, screened and also unscreened or raw data. And we used the reference case to compare the other cases with the reference case to select the best scenario, best study. The imbalanced data set in the reference case was augmented and balanced with the data set that we generated in the 4 study cases, and then we trained the classifier on each of these cases, and then we did the classification using the same data set, and we compared the metrics. The metrics that we used was the micro-average precision score, multi-class precision recall curves, and also net improvement in true positives. All the 3 metrics consistently selected case 3, which was unconditional GAN with unscreened data. There is an interesting point here that I like to mention and highlight here. When we discard the low quality bits in screened cases, we actually change the distribution of the generated data sets. In unscreened and raw data set, the augmented data set is actually composed of the data set with all the same distribution, while in the screen data we add data set with a different distribution to the original data set with a different data set distribution. So in screen cases, actually our training data set is composed of 2 sets of data with 2 different distributions. This would impact the training, I mean the convergence, the optimization in a negative way. So this is a point that we should take into consideration when we screen data. On one hand, we get a better quality data. On the other hand, in training, we are dealing with a training set with 2 different modalities and 2 different distribution, which has a negative impact. The codes of this particular research, as well as our other researches, are available on GitHub. They're public domain and can be downloaded anytime. If you had any question regarding the codes or the paper itself, please don't hesitate to contact me. I will try to address them as soon as I can. If you didn't have any question, just shoot me an email and let's stay in touch. That would be much appreciated.